Oh. We live in a world filled with electricity. It's in every rock, it's in the sky, it's in the food you eat. It's even in your body. If you don't believe me, drag your feet as you walk across the carpet. Then reach out and touch something metal. Ow. People have known about electricity for thousands of years, but it's only in the last 200 years or so that we've discovered ways to make it useful. What was the key? Circuits and switches. We had to find ways to channel the electricity to make it flow where we wanted it and be able to shut it off when we didn't want it. But first, we had to understand what electricity was. Our world is made up of atoms, and every atom is a balance of positively charged protons and negatively charged electrons. Electrical current flows when the electrons jump from one atom to the next. Some materials like copper and silver conduct electricity very well. Their electrons jump around easily, so we call them conductors. Other materials are non-conductive. Their electrons resist jumping, so electricity doesn't flow through them. Materials like rock, wood, or rubber are called non-conductors. Non-conductors or insulators are important in circuits because they keep the electricity from flowing where you don't want it. They insulate you from electricity. All circuits consist of 4 parts. First, a power source that sets electrons in motion. Keep in mind the power source doesn't produce electrons. It's more like a pump that pushes electrons through the circuit. Second, you need a conducting path, wires made of conductive material that can carry the flow of electrons from one side of the power source to the other. If there's a break at any point in the conducting path, the electricity will stop flowing. Third, you need the electrical load, which is where the electricity does its work. Whether it's lighting a bulb, heating a room, or powering a video game, it's a load. After all, if you go through the trouble of making a circuit, you want it to do some work. Of course, if you didn't like what your circuit does, you need the 4th part, a switch to shut off the power. Can you imagine never being able to turn the electricity off? That's almost as bad as never having it at all. Now that we've covered the circuit basics, let's look at some of the amazing circuits engineers have designed and built. We'll start with a report on a circuit that's part of your life right now.
My goal was to find the biggest circuit, and I think I found a pretty good candidate. This circuit is so big it covers a large portion of North America. Now, it's much more complex than the tabletop circuit you may build in your classroom. It's got lots of power sources and a web of wires, but it works on the same principles. We're standing here at the base of one of this circuit's power sources. This dam stands almost 300 feet tall, but it's really just a power source like the battery in your tabletop circuit. Where a battery produces a small flow of electricity using a chemical reaction, machinery inside this dam produces a huge flow of electrons that can run for thousands of miles. Loud in here, huh? This is where the electricity is produced. Water falling at great pressure spins these turbines 163 times a minute, setting electrons in motion. And because electrons move at the speed of light, they can travel huge distances in a fraction of a second. And remember, this dam is just one of the hundreds of power sources in our circuit. More than a single line, this circuit stretches like a huge spider web that covers 14 western states and 2 Canadian provinces. Now, this is one of the major crossroads right here. One of these lines goes all the way to Canada, and another one reaches the Mexican border. The power's ultimate destination is determined in the utility company's power control center. By simply flipping a switch, operators can divert the power to anywhere on the grid. The primary connectors in these regional power grids are giant transmission lines that take the electricity long distances from power plants to substations. At the substation, transformers reduce the power's voltage so that it can be safely transmitted over smaller power lines. These distribution lines then carry the power to individual schools, homes, and businesses. And that circuit doesn't end till it reaches your home. We take it for granted, but our modern lifestyle depends on every part of this circuit working perfectly. And what happens if something fails? We're all in the dark.
Thank you, Rebecca. So now that we've got the electrons flowing and explored the granddaddy of all circuits, what does this have to do with computers? Brahman has that story.
This circuit looks similar to the one we saw earlier, but if you look closely, you'll see one important difference. I've installed a different switch. What's interesting though is that this switch has no moving parts. It's called a transistor and it works by an electrical charge. Add electricity here and the current flows. Take it away and the switch is open. Now, how does this work? How can a transistor possibly turn a circuit on and off without any moving parts? Well, remember, Annette mentioned that the world is made up of two kinds of materials, electrical conductors and insulators. Well, really there's a third group of materials that can be made to conduct electricity under certain conditions. We call them semiconductors. Let's go over to the blue screen and I'll show you what I'm talking about. Okay, silicon. One of the most common elements on Earth is a semiconductor. Now, under normal conditions, silicon is non-conductive. But when you mix in different elements like boron or phosphorus and then add electricity, silicon becomes conductive. Here's how. This is a cross-section of a transistor. The bottom layer is silicon, and when a positive electrical charge is introduced into the transistor, it attracts negatively charged electrons into a channel through which electricity starts flowing. When this happens, the switch is on. Remove the electrical charge and the switch is off. It's as simple as that, a switch with no moving parts. It led directly to the microprocessor in today's powerful computers.
Whether a circuit spans a continent or is the size of your thumbnail, whether the switches are giant levers or microscopic transistors, all circuits work basically the same way. By understanding how circuits work and how they could control the flow of electricity through those circuits, engineers set the stage for a technological revolution.